Okay, I think, okay, we'll try it this way. Okay, so it's our pleasure to have Keter Murch talking today, and I'll say a few words about his scientific trajectory. So Keter actually received his bachelor in physics from Reed College in 2002, and then he went on to do his graduate studies at Berkeley, working with Dan Stemper-Kern, who actually also spoke here to us at the seminar a couple of weeks ago. And there he worked on Bose-Einstein condensates, cavity quantum electrodynamics, and quantum measurements, which I guess is a theme that we'll also hear about today. And then Keter actually stayed at Berkeley for a postdoc with Irfan Siddiqui before then starting his own group at Washington University, where he is now an associate professor and works on like fundamental questions in quantum mechanics. And his work actually has earned him a number of prizes, including an Alfred Sloan Fellowship in Physics in 2015, an NSF Career Award, and a Cottrell Scholar Award in 2018. And today we'll hear him again on another topic of fundamental quantum mechanics, and that is exploring the frontiers of measurement and dissipation with microwave quantum circuits. Keter.
Great. Thank you for the introduction. And since it's a small group, and since I love to have questions, feel free to ask questions, interrupt me as I go along, or if you want to stick questions in the chat, you can do that as well. I've got that open, so if you're feeling timid, feel free to put questions in there. And hopefully we can talk about some interesting science in the next hour or so. So dissipation and decoherence are quintessential aspects of quantum optics. That is, if you have an atom by itself, okay, it's great. So some sort of closed quantum system undergoes unitary evolution according to the Schrodinger equation. But there's no optics, it's just an atom, right? In order to have light and quantum optics, therefore, we need to consider systems that are necessarily open to the environment. And so we have to think about the coupling between this atom and its environment, some sort of radiative interaction. And that radiative and dissipative interaction with the environment leads to really three things, maybe. One is it gives the atom some lifetime. So if it starts off, say, in its excited state, it decays down with some decay time, okay? And then it also causes these energy levels to have a line width associated with them. So lifetime and line width. And a consequence of this interaction with the environment is that we can no longer sort of treat the evolution with a Schrodinger equation for a wave function, that instead we have to treat this with a master equation treatment for a density operator rho. That is, you might consider an experimental situation where the atom starts off in its excited state, and sometime later it's in its ground state because it's decaying with some lifetime. But in between, we don't know what state the atom is in, and therefore we describe it with a mixed state description, requiring us to use a density operator rho. Okay, so the mixed state description really just reflects the fact that we don't know what's going on. And when I guess early thoughts about quantum theory, this idea that you don't know what's going on or that the system isn't in some sort of exact state could be kind of troubling. The idea that the Schrodinger equation no longer applies. And that sort of question led to the idea of a quantum jump. Question? Yeah, go ahead.
It's just maybe statement, because in quantum mechanics, we certainly knows what's happening between, because we have a complete set of wave function of atomic, for example, yeah. And then I will use combination, yeah, and calculate probability to have amplitude of specific state, yeah, C as function of T. After this,
right.
It seems it's technically impossible, I know, but it looks that theoretically it's absolutely known, yeah, what's going on in between.
Yeah, I guess the point is, we want the idea is to replace these question marks, what's going on in between, with something more concrete. And so I think to the point that you're making, maybe one way to do that is that this quantum jump picture, that we can think about the evolution from its excited state to its ground state as it evolves along in the excited state and then abruptly then jumps to the ground state, and this is the ground state. So at all points, you can consider that it's described to be in a state described by a wave function or an eigenstate of the system, or some sort of specific
Sorry,
ket.
maybe I'm not agree in what aspect, yeah. This step which you show, if I will use complete set of atomic wave function and will have information about thermostate environment, yeah, I will write equation for amplitude of each excited state, yeah. Schrödinger equations, this, yeah. And after this, I will solve, theoretically speaking, this time-dependent equation. Instead, this jump, yeah, I will have a contribution of other excited state and smooth development from one state, excited state, to ground state at the end. Yeah. This is time-dependent perturbation theory. What's the question for me?
Okay, so I think you're saying that, you know, when we consider the atom and then all the modes of the environment and how they evolve coherently, we can write down a complete description of the system. You're muted.
Yeah, if your environment certainly unpredictable, if you don't know property of thermostate, I agree. Yeah, it would be question mark. Yeah.
Okay. Great. Well, I think we're going to get right into those issues. So bear with me. So the idea of this quantum jump is that the atom, makes an abrupt jump from excited state to the ground state, sort of description of a quantum jump between two states. And the idea is that that quantum jump happens at different times. And so it's sort of the randomness of this jump time that replaces those question marks that we had before, given our uncertainty about the state. But the idea is that somehow inside what's happening is really jumping between these two states at discrete times. I want to take a moment to sort of dig into this idea of the measurement of these quantum jumps. So to the point of the system is interacting with the environment, what does the environment tell us about the evolution of this quantum system? So imagine a situation where the atom is in its excited state, and it decays by emitting a photon into a single mode of the environment. And when we think about that emission of a photon into the environment, we usually think about what would happen if we put a detector there that detects that photon, right? And so we can imagine this detector to be, say, a photomultiplier tube, something that gives a click when it detects the photon. And that sort of detector tells a very specific story about the evolution of the atom's state. That is, the atom starts off in the excited state, the detector is quiet, excited state, excited state, excited state, until we get a click, at which point we know that the atom has emitted a photon into the environment, in which case we know that the atom's undergone a quantum jump to the ground state. Okay, and then now we notice the ground states, the situation is a little less interesting. There's no more photons to detect, and the story is over. Okay, so that tells the story of a quantum jump happening associated with the detection of a specific click with your photon detector. A hypothetical experiment, but one could imagine an experiment where you try to do this. Okay? But here's an interesting thing about light, is that light has a wave particle duality. That is, there's a particle nature of light, which is what we're detecting when we think about detecting photon clicks. But there's also a wave nature of light, which pertains to the interference of light waves. Okay, and so when one measures the wave nature of light, one performs something called a homodyne detection. That is, we can imagine interfering the fluorescence from this atom with some sort of local oscillator at the same frequency, and asking, is there constructive or destructive interference? So this is actually an experiment we started in 2014 when I started my group at Washington University. And so we set up a device to, rather than measure the photons emitted in spontaneous emission, to measure the wave nature of the emitted light using homodyne measurement. We plug in the apparatus, and what do we measure? Well, we see our homodyne signal turns out to be a bunch of noise. That's not particularly unexpected, because in the quadrature space description of light, we have there's the sort of vacuum state has some sort of minimum uncertainty state. It has some quantum noise. And so when we measure with the homodyne detector, what we're measuring is one of these quadratures of light, say the position or the momentum quadrature, and it's given by a Gaussian distribution. So we have zero mean Gaussian distributed white noise. Okay, well, what does this noise tell us about the state of the atom as it undergoes this quantum jump? It's a very different signal than the sort of discrete clicks that happen at random times. Well, before I answer that question, let me just back up a little bit and say some very basic things about how we talk about measurement in quantum mechanics. Okay, so we're talking about an atom. So far it's had two levels, so we'll call it a qubit. And we're going to represent this with the language of pseudo-spin half, because there's two energy levels. And so let's say we prepare this qubit in its ground state, say spin up, and then we measure, well, then in that case, we know that the expectation value of the sigma z Pauli operator is +1, okay? And you can ask, what's the expectation value of the sigma x Pauli operator? Well, it's 0, and that's because spin up in the z-axis is a superposition of up and down in the x-axis. Okay. Fine. So let's say you measure the x component of the spin. So we measure sigma x, and we get a certain eigenvalue of that measurement operator. Well, now we know that the spin is up along the x-axis. And this has two effects. One effect is to change the expectation value of sigma x from 0 to 1, because we've learned that now it's spin up along the x-axis. But it also has a different effect, which is to change the expectation value of sigma z from 1 to 0. So the point is that measurement has two effects. One, you can gain information. You change the expectation value of sigma x from 0 to 1, reducing the uncertainty in sigma x. But we've also changed the expectation value of sigma z from 1 to 0. So one is information, one is a back action. Okay. Just to make this a little more complicated, one could think about a sequence of these measurements in time. So we'll measure the z-axis, x, z, z, x. Each one of those gives an eigenvalue. And then from that, I can plot in time the expectation values of this qubit in accordance with all those measurement results we've achieved. Okay, so expectation value sigma z is 1, then it's 0, then it's -1, and so forth and so on. Okay, just to make it even more complicated, we could imagine, rather than projective measurements of the spin component, we can imagine weak measurements. We're measuring some general measurement operator M1, M2, M3, and each one of those gives me some measurement outcome, little m1, little m2, okay? And we could use these to track the evolution of the state, maybe not in a described exclusively by a wave function, but in fact by a density operator. So one element of that density matrix might evolve in time accordingly with all of these measurement results. And so this time evolution of this quantum state is what we call a quantum trajectory. It's how the measurement outcomes update our knowledge about the state. Okay, so that's the story of quantum measurement. So back to my question, we have this homodyne signal where we've measured the photon emitted by the atom decaying under spontaneous emission, but we're measuring the quadrature amplitude of that light rather than the photon click. But each one of these little bits of noise can be thought of associated with it a measurement operator. So this is some set of measurement operators, and I won't get into the details of what they are, but each one of those measurement operators allows me to calculate a piecewise continuous trajectory for the density operator description of the state. And so from that, I can calculate the expectation value of sigma x, expectation value of sigma y, expectation value of sigma z. So what do these trajectories look like? So one noisy measurement record allows me to calculate one trajectory of the state. So it starts off here in the excited state. And we see the trajectory is, instead of jumping abruptly from the excited state to the ground state, it's taking some sort of diffusive path as it decays through its state space. Okay, if I do the experiment again, I get a different sequence of noise, and I get a different diffusive quantum trajectory transitioning between the excited state and the ground state.
Keter, when
Yeah.
you say diffusive, are you thinking about, or are you describing just, or are you using the term loosely in describing qualitative aspects of the trajectory, or does this literally have characteristics of a solution of a diffusion equation?
I'm using it somewhat loosely. So it's the say the x coordinate of the state, the expectation of sigma x has a distribution that grows in time. It's being driven by these the fluctuations in the signal, which are Gaussian distributed. So this has a lot of the same physics of diffusion, but then the sort of this shape of this state and the Bloch sphere and the structure of the measurement operators sort of cause the diffusion to be faster or slower depending on where the state is, as it's constrained to sort of maintain the Heisenberg uncertainty relation between the different observables of the system. So somewhat loosely, but somewhat precisely. How about that?
Okay, thanks.
Yeah.
I would like to ask also a question about trajectories. Yeah, it's very nice to have some principles. For example, least action principle. You remember in quantum mechanics, you have also. Do you have some principle for this trajectory? How they fluctuate near average, or what least action or something like this?
Absolutely. So, excellent question, and that's a question that I've collaborated with Andrew Jordan, a theorist at University of Rochester, for many years. And so one could ask, here we have a trajectory from one place to another, okay? And in classical mechanics, the principle of least action tells us the correct trajectory between these two spots. But in the quantum trajectories, they don't ever follow this thing, but one can ask, what's the most likely trajectory? And so if you choose a certain initial location and a certain final location, one can calculate what's the most likely trajectory that connects those two places. And that follows the same sort of exact mathematics of an action principle argument. And it's very interesting stuff. So we talk about that in terms of the probability distributions of trajectories. Okay,
so maybe maybe another question. Like now you can probably like also assign a time like to emit the photon.
So let me I'll reflect on the comparison between the two in a moment. The one thing I can say about that is that the steps that the state chain makes toward the beginning, when it's an excited state, are larger than when it gets toward the ground state. And if you think about what the probability for it to emit a photon is also decreased, it's the highest at first and less later on. And so the measurement dynamics are stronger when it's toward the excited state than toward the bottom. But the description of a photon at a certain time doesn't apply here. We're thinking about the quadrature amplitudes of this light rather than the particle nature of the light. Mm-hmm. So to compare these two descriptions, we had one picture where we sort of imagined detecting the photons emitted by the atom with the photon detector that clicks at certain times, and those clicks are associated with jumps from the excited state to the ground states at discrete times. But in this other picture where we measure the quadrature amplitude of the light, we get this noisy signal corresponding to the quantum noise associated with a photon over some bandwidth, and we get instead this diffusive description of the state, very different descriptions of the quantum state. And these are what we call different unravelings of the master equation. That is, if I average all of these quantum jumps, repeat the experiment thousands of times, I find that all these discrete jumps to average to the expected exponential decay. And similarly, if I average over all of these quantum diffusion trajectories, I get the same, of course, exponential decay. So the same thing happens on average, irrespective of whether we detected photons or whether we detected the field. And those are two different unravelings of the master equation. The trajectories are unravelings, and they show that how the detector detects the field really affects the dynamics of the system. And that's the whole beauty and magic of quantum trajectories. It's not magic, it's physics, but the beauty of it. Okay. Let's see, let's just jump to here. So we talked a little bit about quantum trajectories and these quantum jumps. I want to switch gears now and tell about another project we've been working on, which is not so associated with the trajectories associated with this jump, but actually instead what happens before the quantum jump. You could think about it this way. Let's say you have a radioactive atom and you get to do some research on it and so forth, and then you give it back to the vendor. And the whole time you had it, it doesn't decay. Is there any signature of its radioactivity if it does not decay? Well, we talked about the density matrix description or the master equation. And so one would describe such an open quantum system with something called the Lindblad master equation. It's a differential equation that tells me about the time evolution of the density operator rho. And it has some part that corresponds to the unitary evolution. Maybe there's some drive that's undergoing unitary evolution, but then there's this sort of terms that have to do with the dissipative coupling to the environment. And the Lindblad master equation is so arranged that there's two terms. One of these corresponds to sort of a coherent non-unitary evolution, and one is called the jump term. And an interesting sort of mathematical curiosity is if you somehow were to take the jump term away, the evolution of the system is now follows this unitary evolution plus this coherent non-unitary part. The system evolves according to an effective non-Hermitian Hamiltonian. That is, this thing's Hermitian, this part's Hermitian by construction, but then there's an I here. Okay, so somehow if you take away the quantum jumps of a decaying system, the evolution is described by a non-Hermitian Hamiltonian. And that's exactly what's going to happen right before this jump period here. Question?
Yes. I usually think of the unitary evolution term as the coherent evolution term. So in what way is the final term coherent but non-unitary?
It's let me think about what I mean by it's coherent in that I can write down that a wave function that I have this effective Hamiltonian, and its evolution I can use that in a Schrodinger equation. So it's not mixing the states, it's not adding entropy to the state. So I don't need to, this by incoherent means I'm losing information about the system that I need to use the density matrix description. The coherent part means I can describe it with a quantum state, but a quantum state that obeys a non-Hermitian Hamiltonian.
Yeah, and good example, it's just if you introduce complex value of energy, it will decay of particle, which really some gamma model and other stuff, yeah, which works well, yeah, but coherently.
Perfect. Yes, exactly. So we'll let me show you that. Okay, so non-Hermitian Hamiltonian. When I teach quantum mechanics and we go into any of these textbooks, they'll warn against non-Hermitian Hamiltonians because you end up with complex energies and probability is not conserved and you run into all sorts of problems. So generally we assume that Hamiltonian should be described by a Hermitian operator because we want to maintain real energy eigenvalues, which give us unitary time evolution, conserving probability. The other benefit of a Hermitian operator is that you're guaranteed a set of complete orthogonal eigenvectors. And so that's good for making a sort of basis to describe your state. But when you have a non-Hermitian Hamiltonian, these two things are no longer guaranteed, and that could be a problem or that could be interesting. Okay, so we always say the Hamiltonian must be Hermitian, but my colleague Carl Bender, back in the 80s, or back in the 90s, discovered that if you're really concerned with unitarity, that you have unitary time evolution, that you really want real eigenvalues, you actually can have real eigenvalues even if you have a non-Hermitian Hamiltonian. And he found that it had to do with Hamiltonians that had PT symmetry. So he was studying, as theorists tend to do, some sort of esoteric system like a harmonic oscillator with some sort of complex term added on there. What does this mean? Who knows? But he found that, look, it actually has real eigenvalues for certain values of n. Okay, and actually Carl wasn't the first person to study such a Hamiltonian. There was a mathematician, Manuela Calcetti, back in the 80s, who was studying similar differential equations without really a physical context and finding, yeah, there's real eigenvalues and there's complex eigenvalues, and it's kind of an interesting problem. But Bender's work in '98 really excited a lot of mathematical physicists with this idea that maybe PT symmetry, that is parity time or space-time inversion symmetry, is sort of the more fundamental requirement of quantum mechanics rather than hermiticity of the Hamiltonian. And so following this paper, there have been thousands and thousands of papers sort of talking about PT symmetry and all this interesting stuff that happens with non-Hermitian Hamiltonians that still can have real spectra. And that was very much a theoretical enterprise until a few papers in the mid-2000s helped launch these ideas into some sort of experimental relevance. And that was the identification that this PT symmetry could be realized in systems that have gain and loss. Okay, so the idea is that consider two modes. These could be, say, pendula, pendula A and pendula B. And one of them has gain, that is, something's causing it to gain amplitude. And one of them has loss, something's causing it to lose amplitude. And we introduce a coupling between the two at rate J, that this system has effective PT symmetry. That is, if I flip the two things, that's my parity operator, then the top one has loss and the bottom one has gain. And then I apply time reversal, gain turns to loss and loss turns to gain, we get back to where we started. And so it turns out that gain and loss is a very easy thing to realize in classical wave systems. In fact, Carl Bender, my colleague, who's very much a theorist, so I can say this, built an experiment to demonstrate this effect, where he had two pendula, one is set up to have gain, one is set up to have loss, and he's able to see that this thing has effectively it has real eigenvalues under certain parameters. Okay, there have been experiments with optical microresonators, there have been experiments with electrical circuits, experiments with metamaterials, optomechanical systems, just a huge slew of interesting experimental systems studying effective non-Hermitian evolution with gain and loss. And when I started at Washington University, Carl Bender says to me, hey, can we build some sort of quantum PT symmetric system? Because for all the years that people have been working on this, the realizations of parity time symmetric systems have been in really classical systems, or at best semi-classical systems. So mechanical oscillators, electrical oscillators. Is there a way to make a non-Hermitian quantum system? Okay. And so fast forward some number of years, we were looking at this Lindblad master equation and thinking, what if you can take away this no jump evolution? Then we have a non-Hermitian Hamiltonian. Would there be some way to realize that experimentally? Okay, so the idea is, how do you isolate this no jump non-Hermitian evolution from a decaying atom? Well, you can imagine this atom decays by emitting photons into all 4 pi steradians of space. And so what you have to do is you have to put a detector in every possible direction. And we have to make sure that none of those detectors click. So it sounds pretty hard to do as an experimentalist, but that's kind of the idea, is we have a decaying atom that hasn't yet decayed. And so since I'm a lazy experimentalist, found a way to do this a little more easily, which is the key to being a good experimentalist, to be very lazy. And the way we did that is by, in fact, expanding the Hilbert space of this system. So rather than just having this decaying atom, we'll allow that we'll have a 3-level system where this lower level decays. And we're just going to let ourselves consider the upper 2 levels of this system So this lower state is sort of like the detector that detects whether or not it decayed. So here's the idea. We've got 3 quantum levels now. We'll label them G for the ground state, E for the excited state, F because we like to follow the alphabet. And let's say we started off in this excited state F, and then we allow it to evolve under some sort of effective Hamiltonian. Okay, so it's evolving, we're driving maybe oscillations between these 2 states. Meanwhile, this excited state has a decay to the ground state at rate gamma. Okay, so after some period of time, we'll measure the system and we'll measure what energy eigenstate is it in. So for example, we might find that it's in the excited state. Okay, we might find that it's in the F state, the second excited state. Fine. But if we find that it's in the ground state, that means that it's jumped. And we're going to throw the results away. So we're using post-selection to look at just the experiments where the atom does not decay. Okay, so that's how we post-select on this no jump evolution, just by making sure that it hasn't jumped out of that manifold of states. Okay, so let's get a little more precise here. We've got these 3 levels here, but we're only considering this upper 2 levels here. And this one decays with rate gamma. And then we're going to introduce a coupling between these 2 with the Hamiltonian J sigma x, but at some detuning. So if I write down a Hamiltonian in matrix form for the system, it looks like this. It's a 2 by 2 Hamiltonian because there's these 2 states, E and F. The state E, which is up here, has the potential to decay. So it has an imaginary term on the diagonal. And then there's a coupling between the 2 states. Okay, so what do you do with the Hamiltonian? Well, you find the eigenvalues and the eigenvectors. Unfortunately, because it's a non-Hermitian Hamiltonian, the eigenvalues are complex. They're given by this nasty complex number here, which has an I under the square root, so you can't simplify this any further. Okay, so before I go any further, let's just take a moment to say some really basic things about complex numbers that'll give you some insight into the types of experiments we'll do. So if we go back to math class, the sort of things my 5th grader is learning, perhaps, we can ask ourselves, okay, what's square root of 4? Well, it's 2, or it's negative 2. Although I found out that in some Eastern European countries, you define the square root to be the positive root, something like that, so we don't get confused. But there's 2 possible answers to the square root of 4, right? And then what about if you think about the square root of some negative number, like 2 minus 1i? Well, it's also some complex, it's going to be a complex number, and there's also going to be 2 answers. But to sort of understand what those look like, we actually need to look at something called a Riemann manifold. So here's a complex plane. So imagine drawing it on a sheet of paper. We take another sheet of paper and we draw a complex plane on that. And then we're going to take a little bit of glue and glue the 2 sheets of paper along, say, the minus real axis to make, and then fold the paper to make what we call a Riemann surface. So this surface tells us the real part of the square root function of some complex number z. So if you imagine taking our number 4 that we studied before, so the square root of 4 has 2 values, one where it's positive 2 and another where it's negative 2, right? And the question is, isn't it kind of strange that there's 2 answers, but we have some simple function like the square root? How do you get 2 answers from this? And that's what this Riemann manifold helps us understand, is you ask, well, what's the square root of some complex number that's near positive 2? Positive 2 plus I times epsilon. What should be a number that's close to the real positive 2? And so you can kind of imagine sort of continuously asking, what is the square root of this number? What's the square root of this number? What's the square root of this number? Until you get over to this branch cut here, at which point we pass on to the lower Riemann manifold, lower sheet, and we'll go over here to the square root of 2, where square root of 4 is minus 2. So this kind of helps us understand why there's 2 square roots, but with a continuous function like the square root. Okay, and then of course, if you keep going around, you'll go back up to where the square root of 2, where square root of 4 is 2. Okay, So this is pretty straightforward stuff for anyone who's taken complex analysis. I missed that math class, so I think this is fascinating. One of the fun consequences, or one of the obvious thing here maybe, is if we start up at here where the square root of 4 is positive 2, and we make a smaller loop, we kind of stay on that upper surface. And it's only where the square root of 0 is 0, where there's only one answer, a degeneracy of the square root function, that sort of defines whether you stay on the upper sheet or you go onto the lower sheet. Okay, so there's something special about this degeneracy, 0 for the square root function. Okay, so that all is to say we have a complex energies of the system, and oh, lo and behold, there involves a square root. Okay, and there's 2 energies because it's a 2-state system. So what we do is we take these complex energies and we plot them with Mathematica as a function of the 2 parameters that we tend to tune in our system, which is J and delta, the coupling and the detuning. And so I say, hey, Mathematica, plot for me the real and imaginary parts of the eigenvalues of this system as a function of J and delta. So here's J and here's delta, and here's the real part of the eigenvalues, and here's the imaginary parts of the eigenvalues. Okay, so wow, these look gorgeous. They're these sheets that describe the energy landscape of this system, which has both complex or real and imaginary parts. Now, there's a few things to note. There's a spot here where the imaginary part of the energy is the same for both states. So there's if you think about the difference, delta lambda, the imaginary part of the difference between the eigenvalues is 0. Okay, but that's a place where the real part, there is a difference. So this is a part where the eigenvalue difference is strictly real. Okay, then there's a degeneracy here where both the real and imaginary parts of the eigenvalues are degenerate. And then there's a part over here where the eigenvalues are strictly imaginary and the real part is 0. Okay, so this degeneracy here is something called an exceptional point. And an exceptional point is a degeneracy that occurs for non-Hermitian Hamiltonians, for example. So for a Hermitian Hamiltonian, we call the degeneracy a diabolic point. And we're guaranteed that we'll have. Oh yeah, please go ahead.
So can you just clarify, because I'm not used to, thinking about energies as complex. So when I think about one way to actually, so how do you actually define these energies? One way that I would normally think about defining energies is I measure some spectral function and it has delta functions at each of the resonances. So how is there some spectral function that you can point to that, like, what does it actually physically entail, these complex energies, beyond just the eigenvalues of this matrix?
Right. Okay, so if you recall what happens when you have some state with a certain energy, how it evolves, it gains phase, like e to the minus I e over h bar, right? Mm-hmm. And so the problem with having imaginary energy is that minus I cancels with your imaginary energy, and you get something that where the amplitude of the state or the modulus of it grows exponentially or decreases exponentially. And so the probability, your way of normalization gets messed up. And so that seems like that's a problem, but that's what this means. We have gain, like loss of the state. So the state's amplitude, its mod is decreasing exponentially or increasing exponentially. Now, the real part of the energy, that's easy. If we create some superposition of energy states, this corresponds to the states accumulate phase at different things. So you get sort of oscillatory dynamics. When you have imaginary energies, you get just damped dynamics. So exponential decay or exponential gain.
Yeah,
so I give you a picture of what's
going
on.
But like clearly any, clearly any actual measurement outcome is governed by an actual probability distribution, which, can't actually exponentially grow. And so clearly this post-selection procedure that you've done is making it, more complicated. Like there's an additional ingredient. Like if I just calculate the wave function amplitudes, that's no longer, the only ingredient in a physical outcome. There's also this post-selection, which presumably enters in some kind of conditional probability or something. So, and now once I think about that, it's no longer exactly obvious what these do.
Yeah, so if so what they do is a strange, they add, let me think about how to
maybe another example could help. So another type of system that can realize non-Hermitian quantum mechanics is a photonic crystal. So it's just a bunch of basically wires down which light propagates, and photon number is not conserved. So the number of photons in any one part of this photonic crystal can increase or decrease. That's the gain or loss, sort of just the number of photons there. And so that's the physical action represented by positive and negative imaginary real parts, or excuse me, imaginary parts of the eigenvalues.
Right, and so here's a,
So
maybe state this, go ahead.
Yeah, the same example, yeah. In atomic physics, you know, excited states of atoms, they include the imaginary part, lifetime of the excited state, yeah. And ground state, not. In this case, excited state, yeah, if you introduce lifetime, yeah. In quantum electrodynamics, I apologize, yeah. If you introduce this, yeah, you will have this complex energy. For all excited state, it's only ground state, yeah, doesn't include imaginary part. It's described exponential decay, sometimes non-exponential decay processes, yeah. Finally, all probability comes to ground state, yeah. It's happened not only in quantum mechanics, Boltzmann equation, you know, it's also equation for eigenfunction, yeah. Ground states, Maxwell-Boltzmann distribution, doesn't have any exponent, yeah. Complex exponent. Other states, they have eigenvalues, yeah, with complex part. I mean, it's a general mathematical statement. I cannot prove it right now, but my impression that how to measure this, it's another point, yeah. But theoretically, probably it's proof, yeah, in different areas many times. Okay, thank you for this.
But I mean, I think Jonathan asked a good question, and maybe my lack of a good answer is kind of gives you a sense of how surprising it is that you have complex energies or imaginary energies. But yeah, it corresponds to gain or loss, or probabilities increasing or decreasing. But I'll try to show you one consequence of the fact that we have this complex energy surface that's sort of dictated by this sort of strange topology of these Riemann manifolds, and whether or not we have a good physical intuition for what complex energy means, we'll see that it does something really interesting. Mm-hmm. Or at least I hope you find it interesting.
Thanks.
Okay, so we've got this. The point I want to make is that a normal degeneracy for a Hermitian Hamiltonian, you have a place where the eigenvalues are degenerate, but the eigenvectors are guaranteed to be orthogonal. In contrast, for an exceptional point, that is a degeneracy from a non-Hermitian Hamiltonian, is a situation where the eigenvalues are degenerate and the eigenvectors are degenerate. One could say that the matrix is no longer diagonalizable at the exceptional point. Okay, so there's been a lot of research on these exceptional point degeneracies, and I have to restart my share. Sorry. All right, we're back. And there's a whole bunch of interesting phenomena having to do with these exceptional points. One is that there's some sort of special transition from having real, purely real, to purely imaginary eigenvalues, discussion of these things called broken and unbroken phases of PT symmetry. There's this degeneracy where the eigenvectors become degenerate. There's some discussion of enhanced sensitivity. Unfortunately, I don't have time to talk about any of these. So I'm going to just jump to one of the craziest or most interesting things about these exceptional points, which is that there's some sort of topological and non-reciprocal features associated with adiabatic parameter transformations on these surfaces. So let me show you what I mean. I'll remind you that we have two tuning parameters that we use in our system. They're things we just tune the lasers with, but the knobs on our experiment. One of those is coupling strength J, which is just an amplitude. And the other one is the detuning delta, which is just a frequency. And at some value of J and delta, there's the degeneracy, the exceptional point. What I want to imagine doing is starting at one value of J and delta, and slowly turning the parameters, avoiding the exceptional point, back to where I started. And I'm avoiding the exceptional point because I want to consider adiabatic evolution of the system. And so I have to avoid the degeneracies, okay? What might happen is, becomes clear if you look at what the shape of the Riemann surface is. It's just like the problem with the square root. We start off in the upper eigenstate. We tune the parameters, we cross this branch cut, we'll end up on the lower sheet, and we'll end up in the orthogonal eigenstate for the same set of parameters, delta and J. Okay, so it kind of feels like a Landau-Zener sweep, except for we're back where we started, but now we're in a different eigenstate. So we'll switch the state from one to the other by adiabatically tuning the parameters. And that's enabled because of the shape of these Riemann surfaces, that I can avoid this degeneracy by going into the complex energy regions. Okay, well, this is the sort of thing that we try to do experimentally. And so the way we'll do that is we'll start off in this state and we'll tune these parameters here. And as we go along, we'll check what is the state of the system. And I'll plot the state of the system in terms of the expectation values of the Pauli operators, just like we had for our discussion of quantum trajectories. Okay, so what do those trajectories look like? They're shown here. So we start off in this state here, which it turns out to be very close to an eigenstate of sigma x. So it's a negative eigenstate of that. So it's down here where expectation about sigma x is 0. And as we tune the parameters and make our whole way around this, we find that we go to the place where the expectation value of sigma x is +1. So we've gone from one eigenstate to the other, but in a fully adiabatic way. Okay. Turns out that all of the wiggles and bumps and noise in this data, or most of them, are well produced by our calculations. And so we can understand that these wiggles here correspond to the fact we're going just a little too fast. And there's a little bit of coupling to the other eigenstate. And so you see oscillatory dynamics when the energy is real, corresponding to the energy difference, and so forth and so on. Okay, but what would happen if we make a smaller loop? That is, we start down here and make a loop where we just come back to where we started, not going around the degeneracy. Well, I asked my students to do it, and so here's the data. What we find is that it stays in the same state. So I make one parameter loop where I go around, I come to the other state. But if I make a parameter loop where I don't go around the exceptional point, then of course nothing happens. And that again points to the fact that there's something special about the degeneracy. It's where this branch cut starts, where we end up going from one sheet to the other sheet. Now my thing's telling my headphones are going to run out of batteries. Let's see here. Is this the right one? Oh, that's the left one. Okay. Let me just, in the last couple of minutes of this talk, say what I just said in a slightly more abstract language. And then we'll make it one step more complex, and you'll kind of get a sense of how interesting this system might be in the near future. Okay, there's in general two parameters in our control space. They call them delta and J, but it doesn't really matter what they are. And there's an exceptional point degeneracy, an EP2, a degeneracy of two parameters in our system that we'll put at the origin of these control parameter spaces. And what we imagined is two loops, one where we start and stop far from the exceptional point. We make a loop that goes around the exceptional point because we're avoiding the degeneracies and back to where we started. Oops. And one where we don't go around the exceptional point and come back to where we started. So where we go around and where we don't. Okay, and so what's happening is we can plot the energies. So here's time on the vertical axis. The energies are in general complex, so we put them on the complex plane. So here's the imaginary part of the energy, the real part of the energy, and we have these two eigenvalues. And if we make the small loop, well, we just tune the energies because we're changing the parameters, but we map one energy to the same one and the other one to, when we come back to the initial parameters. But when we make the loop that goes around the exceptional point, what happens is we've exchanged the two eigenvalues. And so we've taken one eigenvalue to the other, and so like so forth. Okay, so we're just exchanging eigenvalues, but you can see we're sort of swapping them in these complex energy surfaces. Now here's where this is interesting. Is, well, okay, so you point that the control loop can be characterized by a winding number m. So how many times we've exchanged the energies. Is that we actually have more levels of the system. So we have another level of the system, we'll call it h. And so we could imagine coupling these two with some values j and delta, and these two energy levels with some values j and delta. And so there's now 4 parameters we can control. And there's a 3x3 Hamiltonian, which will in principle have a 3-fold degeneracy EP3. So here's a sketch of those 4 control parameters. They're hard to visualize in 2 dimensions, but you can imagine there's, you know, this control parameter, this one, and this one, and this one, and we'll put the third order degeneracy at this origin of this control parameter space. Now, there's also going to be cases where there's 2 second order degeneracies, that is regions of EP2, where 2 of the eigenvalues are degenerate, but not the third. And that's going to be some surface in this 4-dimensional space. Okay, and so now let's imagine some parameter surface, a 3-sphere, so a 3-dimensional surface that's a constant distance from the EP3 origin. Okay, so it's a 3-sphere where the surface is 3-dimensionals, and so if it's that I can sort of visualize by turning that, by doing a stereographic projection into Cartesian space. So this cube represents the parameter space that's a constant distance from the exceptional point, EP3 at the origin there, right? And this cube intersects the EP2 surface in a certain place. And one thing that's kind of interesting is that EP2 surface turns out to be a trefoil knot embedded in this 3-sphere space of that's a constant distance from the 3rd order exceptional point. Okay, so now when we start to think about adiabatic operations, we can imagine a control loop that doesn't go around one of these lines of EP2, one that goes around one line and one that captures 2 lines of this EP2. And these correspond to different exchanges of the eigenvalues on the complex plane. So there's 3 eigenvalues. You can imagine a path where we just map them to where they started. You can imagine a path where we start at one and we go to the other. We swap 2 of them. Or you can imagine a path where we exchange all 3 eigenvalues. And those correspond to control loop 1, control loop 2, and control loop 3. Okay, so in this case, the control loops are characterized by the non-abelian generators of the braid group over 3 elements. So by slowly tuning the parameters in the system, we're braiding the eigenvalues of the system. And they're not abelian because if you braid this one and you braid this one, that's not undone by unbraiding this one and unbraiding this one. Okay, so very abstract, but this is the sorts of things that we can do in our experiment. And if it sounds sort of familiar to like braiding and topological quantum computing and all those exciting things, I think it is similar, but if you want to ask what the connection is, you have to wait a year until I understand. So with that, and I'm sorry, a few minutes over, but that's the beauty of virtual seminars, is you can leave whenever you want. I want to thank the people who contributed to this work. So Miriam Abbasi is a graduate student who's done all the experiments, worked really hard on this. Wei-Jen Chen is a postdoc working in my group. And Yogesh Yogalkar, who's at IUPUI, Indiana University, Purdue University in Indianapolis, has been supporting us theoretically. He's a very brilliant thinker who can straddle the fields of PT symmetry and dissipative quantum systems. And I'll also acknowledge the former student Matthew Nagalu, who's now at MIT, and of course, fruitful conversation with Jack Harris, who's a really incredible thinker in this area. And I'll thank you for your attention and be happy to take further questions.
Thank you for this very nice talk. Yes, so I'm sure there are more questions, although we've already had quite a few. So just go ahead.
I already asked some question. May we return to this slide with your experiments when you do this adiabatic loop?
Yeah.
It
see, something like this?
Yeah, this one, yeah. Okay, thank you. If you look on this blue curve, upper figure, yeah, experimental.
Yeah.
The probability not comes exactly to 1.
Right.
Absolutely. Is it Landau-Zener type of transition?
So,
because it's very similar to Landau-Zener, even oscillations here, which you have.
So the thing that's different than Landau-Zener is, let's say you have two energies that cross, and you have some coupling between the two, so you end up with one, like you can go map from one parameter to the other, right? Is that what you mean?
Yeah.
The thing is about Landau-Zener is you go here, but the parameter has gone from parameter 1 to parameter 2. What's different than Landau-Zener is we go back to the same set of parameters, yet we're now in the other state. So that's
I'm not agree, because Landau-Zener allows a trajectory in complex plane. You have this pseudo-crossing, yeah, pseudo-crossing, which in complex plane real crossing. If you calculate this, you will see in this complex plane that you have oscillation of the probabilities, and you have additional phase, yeah, which similar to Berry phase. I thought it's just in two-level system, it's all stuff reduced to Landau-Zener. I thought, yeah. The question how you define state 1 and 2, it's another point. If it's pseudo-crossing, state 1 and 2 defined differently, yeah?
Yeah, it's, so I don't know about the Landau-Zener where you picking it into complex plane. So that'd be worth researching, because there's
book, Landau and Lifshitz, yeah. If you look, yeah,
okay.
Time dependent.
Of course, everything's in Landau and Lifshitz. Okay,
yeah,
we'll look at that.
You see also that probability not equal 1, even if you will try to adiabatic stuff, yeah, and never 1, because if you do in loop, it means that you have a little bit non-adiabatic behavior, as Landau-Zener told us. Yeah. Okay.
Right. Good.
But oscillations also, could you tell about the nation of oscillation, which probably similar to regular? You have it on a red curve, for example.
Absolutely. So the oscillations we understand quite well. And that's because when we are changing the parameters here, we just go a little too fast because we're limited in how slowly we can go. So we're not truly adiabatic. And there's some coupling between the two eigenstates. And so we end up, at this point here with some linear combination of eigenstate 1 and eigenstate 2. And so therefore, these expectation values will evolve in time at the energy difference. So it turns out that this frequency of oscillation is precisely the energy difference, the real energy difference between the two states at that point. So if we just go a little slower, we can smooth these out. You can actually do something called super adiabatic control, or where we add additional controls to cancel out those oscillations and those couplings. So there's all sorts of tricks. There's stuff that's well known also from Landau-Zener to make sure that you stay on the adiabatic trajectory and to sort of cancel out the amplitudes for things that go to the wrong side and so forth. So all that applies here. But the thing I still think is different than Landau-Wiener is the fact that we come back to the same parameter space. And so if you do, we go around once, we could come back to the state, modulo some phase factor. Turns out that phase factor is an interesting geometric phase. You have to go around 4 times until you get back to the exact same state. So there's a lot of physics that's similar, I think, to the Landau-Wiener case as well.
Thank you.
Thanks for those great questions.
Are there more questions, urgent or not? Well, then let's thank Keter again for a very, very visual and very interesting talk. Thank you. And actually, there is still like one open slot also for the afternoon session. Like if you want to talk to Keter privately, then please shoot me an email and I'll set up a Zoom meeting.
Yeah, I
Great.
also would like to add, it was very clear